Single-picked preferences over policies. A simple but elegant class of domains involve single-picked preferences over one-dimensional policy spaces. This domain can be used to model political policies, economic decisions, location problems, or any allocation problem where a single point must be chosen in an interval. The key assumption we make is that agents' preferences are assumed to have a single most preferred point in the interval, and that preferences are decreasing as one moves away from the peak. Formally, the allocation space or policy space is the unit interval A equals to the closed interval between 0 and 1. An outcome in this model is a single point X in A. Each agent I in N has a preference ordering greater than or equals to I, i.e. a weak order over the outcomes in the unit interval. The preference relation greater than or equals to I is single-picked. If there exists a point Pi in A, the peak of greater than or equals to I, such that for all X in A, remove the set of Pi and for all lambda, which in the half-closed interval on the 0 side and the open interval on the 1 side. The results of lambda x plus 1 minus lambda times Pi is greater than, in I's point of view, is greater than x. Let R denote the class of single-picked preferences. We denote the peaks of preference relations. Greater than equals to, in I's point of view, greater than equals to prime in I's point of view, greater than equals to, in J's point of view, etc. Respectively by Pi, Pi prime, Pj, etc. Denote a profile and tuple of preferences as greater than equals to, which is in R to the n. One can imagine this model as representing a political decision, such as an income tax rate, another political issue with conservative liberal extremes, the location of a public facility on a road, or even something as simple as a group of people deciding on the temperature setting for a shared office. In these and many other examples, the agents have an ideal preferred policy in mind and would prefer that a decision be made as close as possible to this peak. A rule F which maps from R to the n to A assigns an outcome F of greater than equals to any preference profile greater than equals to. As before, a rule is strategy proof if it is a dominant strategy for each agent to report his preferences truthfully when the rule is being used to choose a point. In contrast to the impossibility result of Gibbard 1973 and Sethers-White 1975 that obtained on the universal domain of preferences, we should see that this class of problems admits a rich family of strategy-proof rules whose ranges include more than two alternatives. In fact, the family of such rules remains rich even when one restricts attention, as we do in this chapter, to rules that satisfy the following condition. We say that the rule F is onto if for all x in A there exists greater than equals to, which is in R to the n, such that f of greater than equals to is equals to x. And onto rule cannot preclude an outcome from being chosen ex ante. It is not without loss of generality to impose this condition. For instance, fix the 2 points x, y in the unit interval and consider a rule that chooses whichever of the 2 points is preferred to the other by a majority of agents, and where X is chosen in case of a tie. Such a rule is strategy-proof, but not onto. Similar strategy-proof rules can even break ties between X and Y by using preference information about other points, X prime, Y prime, and so on, in the unit interval, even though X prime, etc. are not in the range of the rule. The onto condition is even weaker than what is called unanimity, which requires that whenever all agents' preferences have the same peak, Pi equals to Pj for all ij, the rule must choose that location as the outcome. In turn, unanimity is weaker than peer-to optimality. For all greater than equals to in R to the n, there exists no point x in the unit interval such that x is greater than equals to f of greater than equals to in i's point of view for all I in n. As it turns out, these three requirements are all equivalent among strategy-proof rules. Lemma 10.1. Suppose f is strategy-proof, then f is onto if and only if it is unanimous, if and only if it is a peer-to optimal. Proof. It is clear that peer-to optimality implies the other two conditions. Suppose f is strategy-proof and onto. Fix x in the unit interval and let greater than equals to is in R to the n be such that f of greater than equals to x. Consider any unanimous profile greater than equals to prime in R to the n such that pi prime equals to x for each I in n. By strategy proofness, f of greater than equals to prime in one's point of view, greater than equals to in two's point of view, and so on, greater than equals to in s point of view. The result of the f function is x. Otherwise, agent 1 could manipulate f. Repeating this argument, f of greater than equals to prime 1 greater than equals to prime 2 greater than equals to 3, and so on, greater than equals to n is equals to x, and so on. F of greater than equals to prime equals to x. That is, f is unanimous. Finally, to derive a contradiction, suppose that f is not peer-to optimal at some profile greater than equals to in R to the n. This implies that either I1 f of greater than equals to is less than pi for all I in n, or 2 f of greater than equals to is greater than pi for all I in n. Without the loss of a generality, assume one holds. Furthermore, assume that the agents are labeled so that P1 is less than equals to P2 and so on, which is less than equals to Pn. If P1 equals to Pn, then unanimity is violated, completing the proof. Otherwise, let J in n be such that P1 equals to Pj, which is less than Pj plus 1. That is, J less than n agents have the minimum peak. For all I greater than J, let greater than equals to prime, in i's point of view, be a preference relation such that both pi prime equals to P1 and f of greater than equals to is greater than equals to prime in i's point of view than the value of pi. Let xn equals to f of greater than equals to 1 and so on, greater than equals to n minus 1, greater than equals to prime, and by strategy proofness, xn is in the closed interval between f of greater than equals to and Pn. Otherwise, agent n with preferences greater than equals to prime n could manipulate f by reporting preference greater than equals to n. Similarly, xn is not in the half open interval with the open on the f of greater than equals to side, and the closed side on the other hand in Pn. Otherwise, agent n with preferences greater than equals to n could manipulate f by reporting preference greater than equals to prime n. Therefore, xn equals to f of greater than equals to. Repeating this argument as each I greater than j replaces greater than equals to I with greater than equals to prime I, we have f of greater than equals to 1, greater than equals to 2, and so on, greater than equals to j, greater than equals to prime j plus 1, and so on, greater than equals to prime n, which is equals to f of greater than equals to, which contradicts unanimity. Since a strategy proof onto rule must be unanimous, this is a contradiction.